and talking about polynomials. I actually had to review this with my BC kids because a lot of them missed this on a quiz because they forgot what actually a polynomial was. So when we talk about a polynomial, we're looking at a function in the form where you have x raised to different powers. And there are numbers in front of each individual variable x in this particular case. Again, when we talk about the numbers that are in front of your variable, they are called your coefficients. Now, if you remember back from your study last year or back in Algebra 1, when you look at the largest power, in this particular case we're calling it n. N is the degree. So when we talk about a polynomial, we look at the degree. And remember, the degree is the largest exponent for x. And if you remember, we talk about writing polynomials in standard form. We will always want to write them in standard form. And when I say standard form, that means that the largest exponent for x would come first. It's going to lead the pack. The domain, I think I mentioned this when we were talking about domains in the last unit. Domain of any polynomial function is all real numbers. So remember, in interval notation, that's going to be your negative infinity to infinity. You can put negative numbers into a polynomial function, plug and chug, get a number out. You can plug 0 in, get a number out. You can plug positive numbers in and get a number out. There's no place that you would have an undefined value. Polynomial functions. Now, this is the critical thing. To be a polynomial function, you must have powers that are positive, real, and integers. What's an integer? When I say an integer, yes, it's a number. Very good. It is a number. What kind of number is it? Whole number. It can't be a fraction. It can't be a decimal. So remember, and all the exponents have to be positive, and they cannot be imaginary. They have to be real. So, for example, take a look at a. Can we consider a to be a polynomial function? Are all of your exponents positive, real, and integers? Yes, so it is a polynomial. Is pi, those of you that looked at pi, is pi an exponent? No, so that's okay. So again, you can have an irrational coefficient, but the powers. So look at b. Is b going to be a polynomial function? No. Why not? You have a negative exponent, and what's another reason? E. Remember, e is an irrational number, which is a decimal. All right? So if a polynomial function is factored completely, so remember the way you solve polynomial equations, you try and get it factored form. You then just simply take each factor and set it equal to 0. We have lots of names for the solutions of polynomial functions. So if you can factor and r is a real number, then r is called a real solution or root. So if you have a solution that is a real 0, then remember we have several names we can use to describe that solution. We could call it a solution, an x-intercept, root, or 0. So if you remember back from Algebra 2, your algebra teacher should have described to you that all of these vocabulary words describe the same location on the graph. It's where the graph is crossing the x-axis, it's a solution. You find them all exactly the same way for polynomials. You factor, set each factor equal to 0. Remember, x minus r is not a solution. This is a factor. You get the solutions from the factor. So, for example, they've already done the factoring for you. So what are your zeros going to be for this particular function? Your zeros are going to be what? -1 and +3. What are your factors? What are your factors going to be? X plus 1 and then your x minus 3. Some of you did the same thing on your test. When the directions say to solve, you're not solving. You are leaving it in factored form. You're not. Remember, make sure you understand the difference when I say factor versus solve. All right, when I solve, that means you factor, you take each factor set equal to 0. Some of you are still just leaving it in factored form, and you're not actually giving the solutions. They say to solve, you've got to give me those zeros, you've got to give me those solutions. So please make sure you understand the difference between factors versus just solving. If you have a factor that occurs more than once, then we can say that R is a repeated or double zero. And if you remember from last year, something special happens graphically when you have that repeated root, which I'll remind you and review here in a few minutes. If R is a zero of even multiplicity, so now let's talk about multiplicity for a minute, a topic you talked about last year back in Algebra 2. If your polynomial is in factored form, so going back to example 1, x plus 1 times x minus 3 squared. The multiplicity is the value of the exponent of the factor. So right here, you've got a multiplicity for x plus 1 of 1, and you've got a multiplicity of 2 for x minus 3. It is the value of the exponent of the factor. We call that the multiplicity. So if you've got a factor that has an even multiplicity, then graphically it does not change from one side to the other. The graph is just going to touch the x-axis at R. So for example, at 3, I have an even multiplicity for this particular function. So what that means is that the graph is just going to touch the x-axis at 3. It doesn't actually make that crossover. It just touches at 3. So if a factor has a exponent of a 2, a 4, a 6, an 8, I know on the x-axis it's just going to touch. If the 0 is of odd multiplicity, the sign of f of x will change from one side to the other. The graph will cross the x-axis at R. So for example, looking at this particular example, the factor of x plus 1 has an odd multiplicity because 1 is an odd number. So then at negative 1, I know that the graph will actually cross over. So when you're making your sketches of polynomial functions, you've got to pay attention to the odd and even multiplicities. Clearing some cobwebs out of those heads, sound familiar a little bit, the crossing and touching bit from last year? So another theorem you guys talked about was the relationship to the degree of the polynomial and the number of turning points. Anybody remember that relationship? If you have a fifth degree polynomial function, what's the maximum number of turning points? 4. Why? Remember, if you have a function of degree n, that at most you're going to have the degree minus 1 turning points. It doesn't necessarily have to have exactly that number of turning points, but it won't have any more. So for example, if you have a 4th degree polynomial function, the most turning points you could have would be 3. It may have 2, it may have 1, but it can have no more than 3. All right, it doesn't necessarily have to have exactly 3. So as I mentioned before, we're going to talk about the end behavior. For a very large number of x, we say as x approaches positive infinity. Or for very small numbers, we say x approaches negative infinity. What affects this is the degree of the polynomial and the leading coefficient. So again, remember, a is your leading coefficient. So if you have an even degree, so again, remember, n is your power for x. If it is an even degree polynomial function, now when I say a is greater than 0, does that mean it's a positive number or a negative number? Positive. So if I say I have a positive leading coefficient, and it's an even degree function, then the graph will open up to the right and up to the left. Both ends go up. If the leading coefficient is negative, and it's an even degree polynomial function, do you remember what happens with the ends? So both going up, they're both going to do what? Go down. So that's the end behavior of your even degree polynomial functions. If you have an odd degree, so the power for x is odd, and again, a is still your leading coefficient. So again, if a is greater than 0, I'm dealing with a positive leading coefficient. Then the graph will go up to the right and down to the left. If the leading coefficient is negative, it reverses. So it'll go down to the right, up to the left. So to kind of put a picture to what I just described to you, if you have a positive even power, both ends will go up. Doesn't matter how many bumps and turns you have in the middle. If you have an even degree polynomial function, both ends go up. So we would say the end behavior is as x approaches negative and positive infinity, both ends are approaching positive infinity. If you have a negative even power, like I just mentioned, both ends are going to go down. Doesn't matter how many bumps and turns you may have in the middle. But if it's an even degree polynomial function where the leading coefficient is negative, both ends go down. So we say that both ends are approaching negative infinity. So now going to your odd degree polynomial functions. If you have a positive leading coefficient and it's an odd degree polynomial function, again, doesn't matter how many bumps and turns you have in the middle. One side will go up and one side will go down. Now, when I say as x approaches negative infinity, what side of the graph are you going to look at for its end behavior? Where is negative infinity? To the right or to the left? Left. So I'm looking on the left-hand side, because that's where all your negative x values are. So when I look on the left-hand side of the graph, what would I say the end behavior is going to be? Positive infinity or negative infinity? Positive. This side's pointing down, so it's going to go towards what? Negative infinity. As x approaches positive infinity, since all of your positive x values on the right, you're looking at the right-hand side of your graph. So on the right-hand side of this graph, all the way to the right, what direction is this approaching? Positive infinity or negative infinity? Positive infinity. Okay? If it's a negative leading coefficient and it's an odd degree, it switches. So that I would say as x approaches negative infinity, again, I'm looking on the left. Notice on the left-hand side, this graph is pointing up. So I would say it's going towards positive infinity. As x approaches positive infinity, I'm looking on the right. Notice on the far right, it's pointing down. So I would say it's going towards negative infinity. Sound familiar from what you guys did last year? Okay. All right. So like I said, when we talk about end behavior, we're going to use another notation. And this is how we describe end behavior when we start talking about limits in calculus. As x approaches positive or negative, it may approach a fixed number, y equals L. So if your end behavior is not positive infinity or negative infinity, it's approaching a fixed number, which we call a horizontal asymptote. And you guys talked about horizontal asymptotes last year. And the definition of a horizontal asymptote is actually a calculus definition. It's the end behavior of the function. So what we do is we describe it as the limit. Again, we're describing the y values. So we would say if there is a horizontal asymptote, the limit as x approaches infinity is L, which is your horizontal asymptote, if it has one. So you would look on the right-hand side, and if there's a horizontal asymptote, your answer would be the value of the horizontal asymptote. Or the limit as x approaches negative infinity. You would look on the left-hand side and look at the end behavior on the left. And we would say it's L if you have a horizontal asymptote. If you do not have a fixed number, we look at the end behavior, which means it could be positive infinity or negative infinity, like we just looked at. So like I said, the only thing that's different is a notation. When you see as x approaches positive or negative infinity, you're looking at the end behavior. Your answer is the end behavior, which will be positive infinity, negative infinity, or a horizontal asymptote. Those are the only three things that could happen when we're talking about the limit when you're approaching infinity. So the way this notation is read, it's the limit as x approaches infinity is L, which is the value of your horizontal asymptote, if it exists. Again, as x approaches positive infinity, you're looking at the behavior on the right. So don't let the notation scare you. Only thing, you're looking at end behavior. It's just this is now your big boy, big girl math land now. We're going up. We're getting into the calculus part of it. All right, but the way you find the end behavior has not changed. Okay? So if you want to look on the other side, instead of seeing x approaches positive infinity, you're going to see x approaches negative infinity. So again, you're looking on the left. So again, you're still looking at the left-hand side of the graph. So we would say the limit as x approaches negative infinity is L, which again is just your horizontal asymptote if it exists. If there is no horizontal asymptote, your answer would be positive or negative infinity. Yes, George?
So when we're writing that out, are we supposed to write L parentheses HA? Or
no, I'm just reminding you that L is the horizontal asymptote in this definition. Okay? So, when we started, I said, how do you find end behavior? All of you said you look at a graph. So if a graph isn't given to you, sketch it. So anytime I ask you about end behavior, you asked about a limit, you've got a sketch of graph. That's the easiest way to do end behavior if it's not given to you. So for example, when they ask you to find the limit, so find the limit as x approaches infinity. They're not asking you to do a graph, but as you just mentioned, we know when we do the limit as x infinity, that's an end behavior. So you've got to think about now what we just talked about. What is the degree of this polynomial function? Is it an odd or even degree? Even. Is the leading coefficient positive or negative? Positive. So what did we just talk about if you have an even degree polynomial function where the leading coefficient is positive? What happens with your ends? They both do what? Up. So I know it's going to have to do something like this. So then the limit as x approaches infinity, I'm looking on the right-hand side. What would my answer be? My answer would be what? Positive infinity, and that's it. So now let's take a look at the limit as x approaches negative infinity. What side of the graph am I looking at? I'm looking at the right or the left? The left. Well, I've already done a and b has the same function. So what's happening on the left-hand side of this graph? It's approaching what? Positive infinity. So any questions on how you find the limit? So if the graph isn't given to you, sketch it. You're looking at the end behavior. So let's look at C. I want to know the limit as x approaches negative infinity. So what side of the graph am I going to be looking at? I'm going to be looking at the what? Left. So now, take a look at this function. Is this an odd or even degree polynomial function? Odd. What's happening with the leading coefficient? Is it a positive or negative leading coefficient? Negative. So now think about what we just talked about on the previous page. What a polynomial function looks like when it's an odd degree and a negative leading coefficient. Remember, the left side will be going up and the right side will be going down. So since I'm looking at the left-hand side of the graph, I want to know the behavior on the left. So what direction is this graph approaching, positive or negative infinity? Positive. Okay? Remember, it's pointing up, you're going towards positive infinity. You're looking at the behavior of the y values for the function. If it's pointing down, it's going towards negative infinity. All right, so any questions on that? All right, the next two, the graphs are given to you. So see if you can answer D and E for me on your own. Okay, so did we end up with problem letter D? Did we end up with both sides being negative infinity? Again, both sides are pointing down, so they're both going towards negative infinity. So then for part E, notice the limit as x approaches positive infinity. Again, you're looking on what side of the graph when you're approaching positive infinity. You're looking at the right. So that's pointing down, so that's why I said negative infinity. And then on the left-hand side, the graph is pointing up, so it's going towards positive infinity. So anytime they ask you about limits, x approaches positive or negative infinity, you're looking at the end behavior. All right? So any questions on that? All right, so now let's go ahead and kind of put all these pieces together and start doing some sketches. Again, when I say sketches, guys, they are going to not be 100% accurate, but there are going to be characteristics that are common in all the graphs. So they've already factored the polynomial for you. They want you to sketch it by finding the intercepts and the limits as x approaches positive and negative infinity. So when they say the limits, we are talking about the end behavior. So in order to sketch a polynomial function, you have to know what the end behavior is going to be. So first of all, they've already done the factoring for you. So at least you don't have to factor. But in order to find the degree of the polynomial, you have to know what the degree would be. In other words, if I was to take these factors and multiply it all the way out, what would the largest exponent for x be? The way you find it, if it's factored in factored form, you add your multiplicities together. So add your multiplicities together. So take a look at the factored form of this particular polynomial. You have a multiplicity of 4, a multiplicity of 3, a multiplicity of 1. So if I was to actually multiply, FOIL, and do everything, the largest exponent for x would be the sum of all the multiplicities of the factors. So what kind of polynomial is this? What's the degree going to be? 8. So I know it's an 8th degree. Now look at your leading coefficient. All of your x's inside the parentheses are positive, correct? There is no negative in front of the parentheses, correct? So what's the leading coefficient going to be? Positive or negative? Positive. So it's an even degree polynomial function because 8 is even, and it's a positive leading coefficient. So what happens when your ends when it's an even degree polynomial function positive coefficient? Both are going to go up. So I know in the end that both ends are going to go up. All right? So now let's talk about the x-intercepts. Well, it's already factored, so how are you going to find your x-intercepts? What do you do with each factor? You take each factor and set it what? Equal to 0. So I'm going to take x minus 2 and set it equal to 0. So what's x-intercept, one x-intercept going to be? X will be equal to what? 2. So I know one's going to be at 2, 0. But now at each x-intercept, you need to know if it's going to cross or is it going to touch. So what was the multiplicity for the factor x minus 2? This has what kind of multiplicity? It's 4, so it's what? Even or odd? Even. So it's an even multiplicity. So that at 2, 0, what's going to happen? Is it going to cross or is it going to touch? Touch. So at the x-intercepts, you need to know if it's going to be crossing or if it's going to be touching. So now let's take a look for another x-intercept. Another x-intercept is going to come from x plus 1 equals 0. So what's another x-intercept going to be? Another x-intercept will be at what? Negative 1, 0. Now what kind of multiplicity happens at x plus 1? Is that an odd or an even degree multiplicity for x plus 1? Odd. So if it's an odd multiplicity, is it going to cross or is it going to touch? Cross. Now, it does cross, and I say it crossed with a kink. If it's an odd multiplicity greater than 1, it doesn't do a straight cross over the x-axis, has a little kink to it, which I'll show you the difference when I do the sketch here. Has a little, I call it a kink. It's actually what we call an inflection point. That's the proper mathematical name for it. It changes concavity at that point. But you'll see what I mean when I go to do the graph. If it's a multiplicity of 1, it just crosses straight over. But if it's any odd multiplicity greater than 1, it does a little curvy thing at the... What's another x-intercept? 1. And again, what's your multiplicity? Is an odd or even multiplicity? Well, what is 1? Is 1 an odd number or an even number? Odd. And this is just going to cross straight over. Okay? So I've got 3 x-intercepts. So any questions on how I found the x-intercepts? Isn't there another intercept to this graph? Besides having x-intercepts, what else do we have to check for? What other axis do we have on this graph? Y-intercepts. So let's talk about the y-intercepts. I don't care what kind of function you have. This hasn't changed since Algebra 1 days. How do you find y-intercepts? You plug in what? 0 for x. So y is equal to 0 minus 2 to the 4th, 0 plus 1 to the 3rd, 0 minus 1. Don't be alarmed if you do get some fairly large y-intercepts, especially if you have a larger degree. Well, I know that negative 2 to the 4th is going to be what? What's negative 2 times negative 2 times negative 2 times negative 2? 16. I know 1 to the 3rd is 1, but 0 times negative 1 is a negative 1. So my y-intercept is going to be at 0, negative 16. Okay. Wait, what? So just label the y-intercept all the way down here at negative 16. You don't have to count all the way down to negative 16, but just label your y-axis. So now I'm going to plot my x-intercept. So I have 1 at 2, 0. I have 1 at negative 1, 0. And I have 1 at 1, 0. You must always, 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 always label your x and y axis. All right? So now you told me the end behavior, that both ends are going to be pointing up. So I know that both ends are going up. So I like to always kind of draw my arrows there on the end. So now let's start making the connections. You told me at negative 1, 0, because it's odd multiplicity, it's going to cross. And I said it's going to kind of cross with a kink in it. So I kind of make that little curve right there. Kind of reminds me of that x to the 3rd graph when I think of that kink. It's going to go down. I know it has to pass through the y-intercept at 0, negative 16. Then you told me at 1, 0, it's going to cross because of odd multiplicity. So it crosses straight over. I don't have that kink at 1, 0. At 2, 0, you told me because it's even multiplicity, it's going to touch. I know it's going to have to come down, bounce off the x-axis at 2, 0, and come back up. Now, the variation that I can't take off for is occurring between 1 and 2. I do not know how high or how low this point is. And without a calculator at this point, you can't find this. When you need calculus to find this point. So when you're doing your sketches, I obviously can't take off. Some of you may have that going higher or lower, and that's fine. I can't take off for that. But there are going to be consistencies among all of our pictures, and that's what I'll be looking for. Your end behavior is happening, going in the correct direction. You're crossing and touching the x-axis in the correct places along with the y-intercept. So any questions on how I did a sketch of this particular polynomial function? Let's take a look at example 4a. Pretty much the same type of problem. Determine whether we're going to cross or touch at each x-intercept. Maximum number of turning points, finding your limits, and then create a sketch. So let's go ahead and do part A. So the 0. So look at it's already factored for you, so give me 1, 0 of this particular function. 1, 0 is what? 4. And what is its multiplicity? 2. So I know it's going to cross. What's another 0? Oh, yeah, you're right. It touches. Just make sure you guys are awake. Because I know that 2 is an even number. What's another x-intercept? Negative 2, 0. What's its multiplicity? 1. Now it's going to do what? Cross. What's another x-intercept? 3, 0. What's your multiplicity? 3, and it's going to cross with a kink. If it's any other odd multiplicity besides 1. So if it was a 3, a 5, 7, 9, 11, they're all going to cross, but it'll cross with that curve point. It's actually called an inflection point.
Even with like this before it was like -1.
Yep.
You have to think it's not.
Yeah, it's a multiplicity. It's not the, it's the multiplicity, not the value of the x-intercept.
Oh,
Okay? Guys, any questions on how I found my x-intercepts? Actually, I already did part B with this too as well. So let's talk about maximum number of turning points. First of all, I have to figure out the degree. How do I figure out the degree? What do I do with these multiplicities? I'm going to do what? Add them together. So what's the degree of this polynomial function going to be? 6. It's a 6th degree. So what's my maximum number of turning points going to be? 5. So 6 minus 1 is equal to 5. So you got to know the degree before you can find the number of turning points. D. Then we would find the limit as x goes to infinity of f of x, the limit as x approaches negative infinity of f of x. Remember, this is just talking about the end behavior. We just talked about how this is a 6th degree. Does it have a positive or negative leading coefficient? Positive. So for the 6th degree, leading coefficient's positive, what's happening with your ends? Both ends are going to do what? Go up. So they're both going to go towards positive infinity. We know it's going to have to do that. Okay? So are we okay with the end behavior? Okay? So now we can go ahead and do the graph. So I know at 4, 0, I have an x-intercept. Negative 2, 0, I have an x-intercept. 3, 0, I have an x-intercept. What's the only other intercept I still have to find? The y-intercept. So how do I find the y-intercept? I'm going to do what? Plug 0 in for x. So then y is going to be equal to 0 minus 4 squared times 0 plus 2 times 0 minus 3 to the third. So y is going to be equal to 16 times 2 times negative 27. Obviously, without a calculator, I'm not going to give you one this big. But negative 864. The larger your degree polynomial, the larger your y-intercept typically is going to be, unless it's 1. So obviously, I don't expect you to count all the way down to negative 864. That's why it's critical that you label your x-axis. So I'm just going to label that as negative 864. Told me both ends are going to go up because it's an even degree polynomial function where the leading coefficient is positive. So what we talk about that's happening at negative 2, 0, it's just going to do what? It's just going to cross, come down, pass through your y-intercept. What's going to happen at 3, 0, which is the next x-intercept? It's going to do a crossover with a kink, come down, hit 4, 0, and come back up. I didn't really make my kink very well, but. As long as I can see that it's not as straight as what's happening at your other one. That's why you want to use a pencil, because you may need to fix it. Yes, George?
Do we always have to find the y-intercept even if it doesn't ask for it?
Yeah. Well, it asked for, didn't it ask for intercepts?
It just asks for x-intercept.
Okay. Well, I'll be asking for y-intercepts, so, okay. Any other questions, guys, on that one? All right, let's take a look at the last one. So, first of all, let's go ahead and find your x-intercepts. Well, now what happens, guys, when I take x squared plus 1 and set it equal to 0? If If I go to try and solve for x, what kind of values do I get here? I get what? They're not irrational, but they're what? When I take the square root of a negative number, what ends up happening? They're what? Imaginary. There are no x-intercepts coming from x squared plus 1. So just because it's in factored form doesn't necessarily mean you're going to have a factor that has an x-intercept from it. Okay? So my next one is going to be x minus 1/2. So my x-intercept here is going to be at 1/2 comma 0. Does that have an... Yeah, go ahead, George.
Can you go over the x squared plus 1 thing one more time?
So to find your x-intercept, I have to take the factor equal to 0, correct? So how do I solve for x? I have to subtract 1, correct?
Okay. Got it. Now it makes sense.
What's the multiplicity, ladies and gentlemen, at 1/2 0? Is it odd or even multiplicity? Even. So what's going to happen at 1/2 0? Is it going to touch or is it going to cross? Touch. So there's one x-intercept. Another one's going to be at x plus square root of 5 is equal to 0. When I solve for x is going to be equal to negative square root of 5. Remember, life is full of not pretty numbers. So we have an x-intercept that's not going to be happening at a whole number. It's going to be a decimal value. Okay? What's your multiplicity that's happening? Is it odd or even at negative square root 5, 0? Odd. So what's going to happen? Is it going to cross or is it going to touch? Cross. And it crosses with that kink in the graph. That's actually part A and part B. Part C. Maximum number of turning points. So tell me, looking at the factored form of the function, what is the degree of this polynomial function going to be? Now this is a trick one. You have an x squared squared. So what's that actual, when you multiply it out, that's going to be what? 4, 8, and then what? 11. So it's 11th degree. So if it's 11th degree polynomial function, what's the maximum number of turning points that it's going to have? 10. So there's your maximum number of turning points. So now we want to find the limit as x goes to infinity of f of x, the limit as x goes to negative infinity of f of x. So we know it's an 11th degree polynomial, which means it's an odd degree because 11 is odd. So now the question is, what's happening with the leading coefficient? Is the leading coefficient a positive or a negative? Negative. So I have a negative right here in front of it. So it's 11th degree, so I have an odd degree, leading coefficient negative. So go back to the previous page if you don't remember. If it's an odd degree polynomial function, leading coefficient is negative. Remember, left side goes up, right side goes down. So the limit then is x goes to infinity. I'm looking on the right-hand side of the graph. What's happening on the right? Is it approaching positive or negative infinity? Negative infinity. The limit is x approaching negative infinity. I'm looking at the left-hand side of the graph, and what is that pointing towards? That's pointing towards what? Infinity. Yes, Leilani?
So the multiplicity being odd or even is going to tell you what each side is, like if they're doing the same thing.
When you add all the multiplicities together.
Okay, but then the leading coefficient tells you if you're starting positive or starting negative.
Yeah. Yeah, so you got to look at both the degree overall as well as whether the leading coefficient is positive or negative. That's what's going to affect your end behavior. Okay? Are we good? Good? Are we good so far? All right, so now we can construct the graph. So we know left side points up, right side points down. We know that we've got an x-intercept at 1/2 0. We know we also have another one at negative square root of 5. Well, the question is, what two whole numbers does negative square root 5 fall between? Well, let me ask you this. What's the square root of 4? Square root of 4 is 2. Square root of 9 is 3. So let me ask the question again. Where is square root of 5 going to fall? Between 2 and 3. So now, if I find the y-intercept, so if I find my y-intercept, I'm going to plug in 0 for x, so y is equal to the negative. 0 plus 1 squared, I know it's just going to be a 1 squared, times negative 1/2 to the 4th, times square root of 5 to the 3rd. So it's not going to be a pretty one. So I have negative 0.5 to the 4th times square root of 5 raised to the 3rd. So I get a decimal of about negative 0.698. So I know it's not going to be quite down here to negative 1. Obviously, I wouldn't expect you to find that something like that by hand without a calculator. So now, what happens at negative square root of 5? Is it crossing or is it touching? What did we discover about the multiplicity? Is it going to cross or touch? Cross. And it's going to cross with that little kink in it. Come down, pass through your y-intercept. What's happening at 1/2? 0. Is it going to cross or touch? Touch. And then it'll come back down. Okay. Yep, George.
So, like, what does the x squared plus 1 squared, like, do?
It doesn't. The only thing it's doing, that's coming from the degree. It's coming from the. It's the degree. It helps find the degree of the overall polynomial. But in terms of graphically, it's not going to